So I want to clean up a couple of things as a part of our process here. So if you recall, the idea was to give a or we're kind of approaching we're approaching an interpretation of quantum in rho in a couple of different ways. So one is to go straight from the Dirac intuition, so the Dirac notation, into rho, and there's some interesting things there. But the other is to start with an interpretation of symmetric monoidal categories, and then extend that to the using Kuka and Kissinger's approach to add the things that make symmetric monoidal category, a presentation of a symmetric monoidal category more specifically quantum. So I gave a rough and ready interpretation appealing to your intuitions before, and I just want to clean up a few details so that we're clear on some things that have to that have to be the case when we do composition. So what we're about is modeling boxes with wires, right? So we have some box and we have some number of ports which you can glue together with wires. And so what we want is the rho-calculus expression that corresponds to a box with wires. And the proposal is that this is some context, and for each input, we're going to have a for comprehension that is in the context. And for each output, we're going to have a corresponding send that corresponds to that port. So let me just stop there and make sure that all of that makes sense. So that means that there's an M plus N hold context K that's taking, a for comprehension for each input and a send for each output. If there are M inputs, then there'll be M holes for the for comprehensions, and if there are N outputs, there'll be N holes for the sends, which gives you M plus N holes inside the context. Does that make sense?
Yeah, so the for is the bra and the send is the kit.
Not quite. So the bra and cat interpretation, I can go back and remind us of that, but I'll that's a slightly different approach. So this is really we're just doing symmetric monoidal categories right now. We're not doing the quantum just yet. But I can show you what bra and cat are in the other interpretation. Okay, so Tomislav, does this make sense to you? Good.
Yes, I'm a little slow today, but yeah.
Okay, all right, good. All right, so the thing that I want to clean up here, let me expand the window so that we can get everything on screen. Is that all on screen for you guys?
Oh yes.
Yeah. Mm-hmm.
Okay. All right. So imagine that we've got an F and a G, and the arity of the outputs matches the arity of the inputs in terms of F and G. So F's outputs, if there are N of them, then there are N inputs for G. And we know how to do a wire in rho-calculus, right? So that means that whatever's coming out here needs to be forwarded to here. Right, so we'll make, so if what's coming out is on the Z, we need to pick that up in some for comprehension and forward it along on the X, right? So if we're using X's for inputs and Z's for outputs, then we pick up the Z, so that would be Z11, Z11, and we forward it along to X21. So if this is X21 here for G, right, we're going to forward that along. And then the wire has to continuously be a wire, right? So it's going to be a fixed point. So this would be a recursive contract, right? Here I've used the mu notation, but you could easily write it as a recursive contract. So that way, if there's more, instead of being a one-off, it can keep doing that job. Does that make sense?
Yeah, I'm following.
Okay, so the same thing here, so we're going to have wires that glue all the outputs to the inputs. Now, the thing that I need to clean up, and this goes back to Samson's slogan, parallel composition plus hiding. So equationally, what we're really doing is, let me duplicate this, and then what we're really doing is we're saying that this is going to be the interpretation of F parallel compose. Whoops. With the interpretation of G. Okay, so far, but notice that we're also going to we're going to compose in all these wires. Okay, so I'll just write a W Z11 X21, right, for the for a wire, right? So here, let me just expand this out a little bit. So we're going to need also to put in a big pi. Just grab a big old pi. There we go. Did that go in? I can't tell. Let me see. No, it didn't go in yet. Hello. Okay then. There. All right. Okay. Oops. Wrong side of the equals. Oh, I see why it's having problems. And so here we want W and Z 1I. Oops, 1I. And X 2I, right? So let me go ahead and make these subscripts. Oops. Okay, and here we want another parallel composition. There we go. Okay, so that's what we're saying the interpretation is. And that's almost correct, right? So let's just go through this. We're saying that F is some box with wires, and we want to compose it with another box with wires, right? So graphically, I have a box, I've got another box, and we wire them together, right? But, well, sorry. And then, so then equationally, what we're going to say is, I'm going to find the interpretation of f, that's this k expression. I'm going to put that in parallel composition with the interpretation of g, that's this k expression. And then I want to put wires between the ports, right? So that's what these w's are. So I've got a w for each one of these expressions, right? Is that making sense so far? So the algebra lines up with the pictures in your mind?
Yeah. Mhm.
So basically, f par g and g par f is the same.
That will be the same sort of, not quite though, because if you run the g, so f par g and g par f is correct, but if you reverse the order, it will reverse these two as well. So you'll stop going from z to x, and you go from x to z. So we don't expect this to be commutative, so we don't expect this to be commutative, and that turns out to be true. Okay, good. So that's almost correct. Can you spot what the problem is? There is a problem. What's the problem?
It's only one wire.
No. That's what this big par is. This
Oh.
par gives you over all the eyes. We're going to get wires for each of the eyes. So
It's not reversible.
no, that's not the issue. All right, I'll give you a hint. What if, is it possible to tap the wires? Yes, it is. The short answer is yes. Right now, the Z's and the X's are free. And so if I inject any other thing that's listening on the Z's and the X's, they could go and mess with the behavior of the wire. Does that make sense? So if I introduce just another output on Z in par with this, that'll screw up potentially, that will compete for the for comprehension that's sitting at this port. Is that making sense?
Yes.
Okay. Okay.
But
All right.
can it be secret?
It can be, and that's what we're about to do. So what we're going to do is we're going to put a new outside. So we're going to do new, and we want to do this for all the Z's and all the X's, right? So so it's, I'll write it this way: Z1I. Oh, I can just cut and paste. Oops. Let me close it out first, then I can paste. Okay, so now I'll have to move it someplace else. There we go. So I'll move it to the left here. Oh, what happened? Oh, I see. Thought I was grabbing the whole thing. So I take that and move the whole thing to the left. Okay.
If we define this in this way,
so remember, so this is over all eyes. So this is like a, a fancy summation convention, right? So I'm really, because I've got indexes down here, it's over all of them, right? So now it closes up these, so nobody else can interact here.
And I wanted to ask if we define this in this way, does it mean that when we if we have some specific I, and then we want to have some I plus one, can this expression
remember remember, so remember, this goes over all the i's,
Mhm.
and it's a different f if you have one more port.
Mhm.
Does that make sense?
Mhm, mhm. Yes, yes. I'm thinking, can we somehow define and say that we will always have the new name, whatever f we put here.
Oh yeah. This is defined with respect to the arity of f and the arity of g.
Mhm, mhm. I see.
Now you have to be a little careful, right? Because now you have to check associativity. Right. So if what we want is that f ring g and g ring f are equal. And will they be equal? Well, yes, they will, because these z's will be different, right? Otherwise, we'd have a wire like this. We'd have a wire from here to here, and then the wire wouldn't be visible. So I urge you to go and check that this is in fact associative.
So before, without the new scope, before it was not associative, but now it is.
No,
associative.
it was still associative. The problem was that we left the possibility for some other box to interact with this one. No, nothing else should, once you wire these two together, you should not be able to interact or tap the wires. Right? So this has to be, it has to become one box with these as the inputs and these as the outputs, and we can't see what's going on here. Right? So when I do the parallel composition, I have to get back a box with wires, a box with input ports and output ports. So I start with F, which is a box with input ports and output ports, and G, which is a box with input ports and output ports. And when I do the composition, I have to get back a box with input ports and output ports. So this expression corresponds to the following diagram. Let me.
And we can say that this is associative because if we wire up, if we have F and G and H, it doesn't matter if we first wire F and G or G and H.
That's correct. That's what associativity means. Now you have to prove that that is in fact the case using this equation. So this new scope is really putting a box around this. So the lexical scope here corresponds to the graphical scope here. Does that make sense?
Yes.
Cool. So we have the lexical stuff matching the graphical stuff. That's good stuff. So then we have this doesn't change, but it is important that we take this into account. So we still have cup and cap to do, but I wanted to go back to Jim's comment here. Let's see. Okay. You were asking the bra and the cat stuff.
Yeah.
Okay, so the way I've got bra and cat defined is like this. So this is a bra and P is a cat. Right, so bra is defined to be this, and that's defined to be that.
Greg, we don't see.
Oh.
If you're showing something.
Oh, sorry. Apologies. Can you see?
Yes.
All right. So, so it's just a quick reminder. So remember that the name of a process, names have all the algebra of processes, right? So in particular, I can define a parallel composition of names to be just, like if this is at P and this is at Q, then I take P par Q, that's a well-defined process, and then I take the name of that. So I define the parallel composition of two names to be the name of the parallel composition, right? It's very straightforward. So that works for the primitive operators like par, but it also works for complex operators like the square root definition that I gave. So we know what the square root of a process is, right? I gave that a few years ago and have revisited that on occasion. And so we can simply define and show that the definition is consistent. The square root of a name is simply to take the name of the square root of the process. Right? So is that clear? Does that make sense?
Mm-hmm. May I just ask you if there is a difference what you are describing here and just normal row calculus? If we have, instead of P, we are sending something on X, and Q is we are receiving something on X. I'm asking because if this is just the process, we can say there is a com event. If this is a name, usually it will not be com event, but are you saying that in your example with here, you're considering this as a com event?
There's no com events here. I'm just giving a definition. All I'm saying is, if you hand me a name, if you hand me a pair of names, I can define par of a pair of names, right? And the way I do that syntactically is, well, since you handed me whatever process you handed me, whether it's a send or a receive or a star at or anything, right? Or another par, it doesn't matter. You hand me a par, you hand me a P, and you hand me a Q. Well, then there is a syntactical thing, which is P par Q, right? That's just syntax, right? Once I've formed this piece of syntax, I can also form this piece of syntax. So this is a process, right? The type of this thing is a process. And the type of this thing is a name.
Now, the name of P par Q and the name of Q par P are the same name?
That's right. They are the same.
And in this context, you are saying even if P and Q can have a com event, this is not important because you're just defining the syntax.
That's correct. Right. We're not running anything. We're just we're doing structural manipulations, not evaluation manipulations. We're not using the reduction operator, just using term constructors. Yeah.
You're defining the mechanism for structuring names?
Yes, what we're saying is that you can lift all of the algebra that is on processes, right? So all the rho-calculus algebra can be lifted to algebra on names in an obvious way. Does that make sense?
Yes.
Yep.
Okay, all right, good. We can also do something that's slightly more sophisticated, right? So I can multiply a name times a process. And how do I do that? Let's go find all the free names in Q, whatever they are, right? Some X, which is a free name in Q, right? Which means it doesn't occur as the left-hand side of a for comprehension. Right? Anything that's not the left-hand side of a for comprehension is free in Q. And again, obviously the new is a binding operator. And so if if we're using the extended syntax, then we have to account for new as a binder. And it is consistent to simply treat new as a binder, but we all know that new is just syntactic sugar for something else. So if we are using the extended syntax, then it would not just be, it's the left-hand side of a for comprehension, but it's also under a new. Okay, so we pick up all the free names, and for every free name, what we're going to do is do a substitution. So it'll be the simultaneous substitution. So we're going to substitute this name, and this name is well defined, right? Why is this name well defined? Well, because of this equation. Right, so I take x and I put it in par with at p, and I substitute this bigger, more complex name for x inside q. Right, so that's the operation of multiplying a name times a process. Does that make sense?
So in a sense, we are creating some version of new, because we are binding all free names.
No, it's not a binder. It's not a binder. It's just we're taking Q, we're making a new Q, and this Q is going to have a bunch of new free names, right? And you can prove to yourself that if X is free, then at P par X for X is free.
And this is also just a syntactical substitution.
Just a syntactic operation.
Okay.
It's like given a process Q and a name at P, we get a new process, and it's defined in this way. Does that make sense?
Yes.
Okay. All right. So you can prove some things for yourself. There's some
Now, why is it called multiplication?
That's a good, you can think of this as like scaling, right? So if X has a certain complexity, then this has a bigger complexity.
I guess I think of that as addition. I don't know.
No, addition would be like adding a process to a process. Think of this as a scalar and this as a vector.
Okay, got it.
Right. Okay, so now there are some lovely properties, right? So obviously, by the definition, this becomes at of P par 0, right? But P par 0 is the same as P, so this is just at of P. So 0 acts as a unit or identity for the parallel composition. And it also acts as a unit or identity for multiplication. Is that clear? Does that make sense?
Yes, basically, whatever free names are in P, if we substitute together with 0, we get the same thing.
Yes, exactly. Right. So therefore, let's think of this operator as a kind of multiplication like this is. So this is multiplying scalars, right? And this is multiplying a scalar times a vector. So now we get a polymorphic multiplication, just like in ordinary linear algebra. Okay, so we can define this, which is just as before, and this. So all we're doing is introducing a little bit of notation. So we're writing star uniformly everywhere, so that we can begin to think of this in a more linear algebra fashion. It's like it's just syntax, nothing fancy, nothing sophisticated going on here. We're writing this for this, right, which is defined to be this. And this, we already gave the equation here. Does that make sense?
Yes.
Yeah, we
Okay.
multiply names and we get a process.
No, when we
Oh,
multiply,
name, I'm sorry. I'm
no,
sorry. I
no.
missed-
When we multiply names, we get a name.
Yeah, okay. I missed. Right.
And so,
I got confused by the middle term there.
yeah, no, that's also a name, right? Right. And so if we treat them as scalars, we know what it means to multiply scalars. When we multiply scalars, we should get a scalar, and we do. And it should be the case that this thing is commutative, and it is. And it should be the case that it has a unit, and it is. Okay. And when we multiply a scalar times a vector, we get a vector. Yay! The types line up.
I would
What's
think that. I would think that the name P in par with the name Q would be a process, and we would have to take the name of that.
No. By definition. So this side of this thing is a definition, right? So what we do is we take P and Q and we form the parallel composition of those two, and then we take the name of that. And so that's the definition, right? So this is a name. These two things are names. So the parallel composition of two names is a name, and we're just taking the multiplication of two names just to be the parallel composition. That's all we're doing.
It's a construction rule.
Yes, that's exactly right. That is exactly right. And so we can multiply scalars, and we can multiply a scalar times a vector. That's why we're saying it's polymorphic. Our multiplication has the nice properties that we want. Okay. So notice that we can also define something a lot like inner product. And the way to do that is to, so if we take a context, so a context is going to be like a dual, so a one-hold context, right? So this is going to be, a context is a process with a hole in it. And so we can always form the application of K to P, which we write with the square brackets. So we put P in for the hole in K. That would give us a process. And then we go and we take the name of that. But we have to do something a little fancy, right? So before we take the name, so we form this process. And then for all the free names in the context and all the free names in the process, we're going to substitute W times X and W times Y. So for all the free names X in K and all the free names Y in P, we're going to do a substitution of W times X and W times Y, where W is the name of P par K applied to 0. And then we take, we can turn a process into its dual. So there is a notion of, there's a notion of duality, right? So in the same way that vectors have duals, and when you take the dual of a dual, you get back to the original vector. You'll see that works here. Right, so we can define the dual of a context to be apply the context to 0, and then you get back to P. And then if you take the dual of P, well, you'll introduce the whole again. Right, so that gives you a notion of duality. And so now we can see that if we take P dot Q perp, that again, by definition, this will give us all the nice properties that we want. So for example, if I take p perp and multiply it by a scalar, we just want that to be defined to be, you take the scalar and you multiply it by p, and then you take the perp. And that will give you all the expected properties that you have of linear algebra. And if, please don't take my word for it. Go and check. So now, go ahead.
Just a little bit clarification of dual. Why is this dual if we add the whole?
So what we want is, so the dual of a process should be a context, right? So if the process doesn't already have a for comprehension in it, so notice that there's a relationship between for comprehensions and context, right? Is that clear? So
Yes.
a for comprehension is waiting for an input, and that input will be a name, and that name can be dereferenced to a process. So every for comprehension is like a process with a hole in it, right? But P might not be a for comprehension. For example, what if P is just a send? All right, so where would I put the hole? There's no obvious place to put a hole in a send. So rather than try to figure out where, I just put it right next to P. Right, I just, for the parallel composition. And then if you check your definitions, you'll see that it gives you all the right properties to do it this way. And the main thing is you have to say how to take the dual of a context, and that's where you have to say that the dual of a context is applying the context to 0, and that gives you it flips you from a context to a process, right? So if I take a process and I turn it into a context, and now I take the context and I turn it back into a process, I should get back to P. Okay, so P, I add a hole with parallel composition, and then I put 0 in for that hole to take the dual of the dual of the context. So that's the dual of the process. Well, P par 0 is just P. So we see that the dual of the process is the process.
Wouldn't the context of the receive be the context of the send?
No, you don't have that kind of duality. It's not the same.
So we're
kind of shifting over into vector space land. Now there is a relationship between the two that you can play around with, and I encourage you to do so, because we know that there's a relationship between a context and a for comprehension, right? We also, you know, so there's a way to dualize a for comprehension, which would be to send a 0 in, right? And that will correspond to taking the dual of the context.
right. It has no context, so we're just creating one.
So if you have a for comprehension, that's like a context, right? And so then you can take the dual of it. Well, how would I do that? Well, I send a 0 in, right? And then that will give me back a process. And that will have all the properties that you're interested in. And again, don't trust me, check the math. So if you have understood those definitions, I can now tell you what a bra and a cat are.
Thank
Okay?
you.
So the bra and the cat are like this. So a process, the cat is going to be just a process, and the bra is going to be the dual of a process, namely a context. And so,
Okay.
now the inner product, or applying the bra to the cat, is going to be, you take the dual of the process, the cat, and you do the inner product with K. So by our definitions, right, that's going to be, it'll be the parallel composition of P with Q scaled by W. That's what it will be.
It makes some sense. I think
Again, all the math is here. You are
Yep.
perfectly free to go and check it out.
a
Right?
little patience for that detail these days.
I hear you. But it's kind of meditative to do the calculations.
Yeah.
All right. So you'll notice that by our definitions, it preserves this identity, right? So if I take some name and I multiply it times a cat, it's the same as if and then I take the bra with that cat. It's the same as if I multiply X times the bra, and then I take the the inner product of that bra with Q, the cat Q. So that gives me the right to extend this notation in the exact same way that I extended, that it is normally extended. So I can put an X in the middle, but more generally, I can put an operator in the middle. So we have to define what operators are, but I won't do that this time. But I do want to point out that this approach, I developed this approach in 2003 on a plane flying back from Las Molinas, well, from Madrid, Spain. So I had already, in 2002, I discovered the rho-calculus. In 2003, it was obvious to me that there's this strange thing going on where contexts look like dual vectors, processes look like vectors, and names look like scalars. But that's different from what's going on here. Hang on a second. Find the other one. It's this one. Yeah, so that's different than what's going on here. Which is, we're just the way we're approaching the way we're approaching this is just to say, okay, so axiomatic quantum mechanics starts with symmetric monoidal categories and then adds to symmetric monoidal categories what's necessary in order to make it specifically quantum. Okay, so we're following in this approach, we're following that pattern, right? So that design pattern. So we say, well, first we have to give a definition of what a box is, a box with with ports on it, and we have to give a definition of composition, and we have to give a definition of tensor. All right, so I should go ahead and make these more precise so that everyone understands.
Very sweet. You know, although I don't grok at all, you know, it seems like you're taking a top-down approach, whereas I'm been working on a constructive approach. You know, starting with a basic creation operator. And I have a feeling that your top down and my bottom up are not too far from hooking up.
It's possible. It's possible. Okay, so now I've given. So what we want to do eventually is to compare what we get this way with what we get the other way, right? So eventually what we'll do is we'll have all of the bits and pieces that you add to symmetric monoidal categories represented as row expressions. And then what we want to do is we want to say, well, how does that math line up with this math? Hang on a second. So how does the symmetric monoidal category interpretation line up with these interpretations? And I want to point out that where we're putting the new is shares an analogy with this scaling by W. W forces that we are locally inaccessible to K or P. And if we only ever have the linear algebra operators to compose our systems, then we will continue this scaling by W will do the right thing in terms of making the wires invisible. So it will act like the new operator that we imposed on the other in the definition of composition. Does that make sense? You understand what I'm saying?
Basically, yep.
Okay. All right. So Dawn, you're here shadowing. Does any of this make sense?
It does. You are way ahead of me. But no, I can follow this. And I need to do more reading. I'm afraid to ask questions because it's probably already documented somewhere. But I think I'm following.
No, it's always good to ask questions, even if it's. I mean, it might be that that what you're having a question about, someone else is having a question about.
Okay, so what was going through my mind as I'm listening to this kind of ties into the question someone else was asking about, inputs, outputs. What I was thinking is, where does temporal fit in? And is that assumed to not exist at this level? And it comes in at lower levels?
No, it definitely does. It definitely does exist. So in terms of inputs and outputs, so here it happens when a process actually evolves. Basically what we're doing is we're setting things up so that a process can evolve. But in quantum mechanics, the evolution only ever happens at a measurement. So all of this is deferred. So basically we're setting up the experiment and then we take a measurement. In normal row, when you put an input in parallel with an output, well, that has the opportunity to evolve so that they communicate. And here what we're doing is we're setting up all the possible communications, but we're not letting them run until we take a measurement.
That clears it up perfectly.
Sure.
Thanks.
Mhm. All right, I'm gonna stop here and give us a few minutes to transition to the developer stand-up. Thank you very much for.
I got one more dumb question.
No worries. Go ahead.
The monadal categories,
Symmetric monoidal categories. Yeah.
monoidal categories would support the notion of this evolution, right?
Yeah. A similar sort of thing is happening. So let me just quickly switch again. I think. So a similar sort of thing is happening, right? So notice that we're not like when we form the composition, we don't actually run the wire, right? We know that if the wire were to run, it would do the right thing, but we're not running the wire, right? And the things will only run basically when you prod the system. And the only in quantum mechanics, the only way you ever get to prod the system is, or poke it, and say, all right, what's going on? Whenever that, the only time you can ever do that is when you take a measurement.
Right.
So that's the idea is that, I mean, in normal row, you put a send next to a receive, and if they share the same port where they're doing their sending and receiving, then they'll go ahead and do what they do, right? But in quantum mechanics, you have to set. You're basically setting it all up. You're setting up the experiment with all these possible information flows, and then you say, all right, now I want to know what's happening. It's like a constraint satisfaction system, right? Now I want to know what's happening at this variable. And so the system runs enough to answer the question about that variable.
Got it.
Yeah, cool. Thanks. All right, folks, I'll see many of you in Dev Stand Up in just a moment.
Thanks, Greg.